I welcome you all for the week 7 live interactive session for the course Chemical Reaction Engineering 2. Now let's get on to the session. So as usual, let's go get on to the brief recap of lectures of week 8. Week 8 had 5 lectures. Lecture 36 was on network of first order reactions, where the first order reactions where n species are participating was discussed, and the vector forms of different components like your reaction rate constant, your diffusivity, and then your Thiele modulus and effectiveness factors and their matrix notation were all explained. Lecture 37 was on use of experimental data for finding out if a particular reaction is external mass transfer limiting or internal mass transfer limiting or surface reaction limiting. So, what parameters helps in identifying any of these conditions limiting a particular reaction, or a combination of these things are limiting a particular reaction? Lecture 38 was on packed bed reactor design, internal and external resistances. Where different configuration of the packed bed reactor was discussed, and then the design equation for a packed bed reactor for first order and second order reaction was discussed, where a problem was solved for the case of the second order reaction. Lecture 39 uh, covered example problem for the packed bed reactor design for a second order reaction, and then the fluid bed reactor was introduced, and the advantages of a fluidized bed reactor was discussed, and what is fluidization and what are the different flow regimes in a fluidized bed reactor were all discussed. Lecture 40 was on was also on fluidized bed reactor design, where Cooney and Levenspiel model was discussed. The features of the model, the factors affecting a fluid bed reactor design. So, for example, the mass transfer rate, the bubble residence time, and the rate of reaction are the factors affecting a fluidized bed reactors. And then the several parameters needed was discussed, uh, that involved fluid mechanics concept, and then the minimum and maximum fluidization velocity and the corresponding formula were were covered, and the assumptions made in the Cooney and Levenspiel model was discussed, and then the gas velocity in the emulsion phase and the bubble velocity uh, formula were all covered in the lecture 40. Now let's get on to the week 7 practice assignment. Match the experimental observation with the limiting conditions for the catalytic reaction from the below. So option A, observed reaction rate is proportional to superficial velocity power 0, diameter of particle diameter power 0, and exponential of uh, exponential relationship with respect to temperature. And then option B, observed reaction rate is proportional to square root of the superficial velocity, and then diameter of the particle to the power of minus 3 by 2, and linear relationship with temperature. Option C, observed reaction rate is proportional to superficial velocity power 0, and then inverse of the particle diameter, and exponential relation with respect to temperature, which is again further raised to an exponential of half. And option D, observed reaction rate is proportional to square root of superficial velocity, diameter of the particle to the power 0, and temperature to the power 0. So what are the three limiting conditions? It is external diffusion limiting, internal diffusion limiting, and surface reaction limiting. Now we have to match, you know, what values of the parameters will say which type of condition is limiting the particular reaction rate. So the answer is option A. The observed reaction rate is proportional to u power 0 dp power 0 exponential of minus e by rt. Is it says that there is a surface reaction limiting. U power 0 and dp power 0 means it's nothing but u power 0 means the value is 1. That means there is no dependency on superficial velocity and no dependency on the diameter of the particle. So the observed reaction rate only depends on the temperature, and it has an exponential relationship with the temperature. That means it is surface reaction limiting. Option B is the observed reaction rate. It is having a square root proportionality to the superficial velocity and dp power minus 3 by 2 and a linear relationship with temperature. Then it is external diffusion limiting, because in the external diffusion only you will have this concept of the superficial velocity, that is the overall gas flow velocity or the fluid flow velocity, which is playing a role in the role in the reaction rate. And then finally the observed reaction rate is proportional to u power 0 dp power minus 1 and exponential of minus e by rt power half. This shows the internal diffusion limiting condition. Okay, and the fourth one was just a random option, so it doesn't have any relevance. Now let's get on to the question number 2. In a fluidized bed reactor, the regime where channels of particles and gas stream are formed with gas escaping through the channels is called dash, and under such condition the drag force is dash than the gravitational force. So we have to find out the regime where the gas, there are channel formation between the particles and the particles which are nothing but the catalyst particles and the gas stream. So the gas stream escapes, there is a channel formed and the gas stream escapes through the channel formed. And uh, what happens to the drag force and the, what is the relationship between the drag force and the gravitational force under such condition? The option is the regime is called as the slugging regime, because slugs are formed, slugs of particles and the gas streams, these channels are formed, and this is called as a slugging regime. And when does this happen? This happens when the drag force, that is the force exerted by the upcoming gas stream, is significantly higher than the gravitational force exerted by the particles in the uh, bed. In that condition only the slugging regime is observed. Question number 3. Identify the order of velocity for different flow regimes in fluidized bed reactor. Option A, minimum fluidization velocity is higher than the slugging velocity is higher than the aggressive bubbling regime velocity. Or option B, aggressive bubbling regime velocity is higher than slugging regime velocity, which is greater than that of the minimum fluidization velocity. Or is it option C, slugging velocity is higher than the aggressive bubbling velocity, which is greater than the minimum fluidization velocity? Or is it option D, aggressive bubbling velocity is greater than the minimum fluidization velocity, which is greater than the slugging velocity? So, which of these options is right in case of a fluidized bed reactor? So, the right option is slugging regime velocity should be higher than the aggressive bubbling velocity, uh, which is to be higher than the minimum fluidization velocity. So the minimum fluidization velocity, it is just the least velocity that makes the particles, the packed particles to start getting fluidized, to start getting suspended in the gas. Whereas, uh, in order to form aggressive bubbles, then the velocity should be higher than this minimum fluidization velocity. And in order to form slugging means we saw that the gas and the particles start moving in separate channels. That means the velocity should be much greater than the aggressive bubbling or the minimum fluidization velocity. So the option C is the right answer. So option C, which is slugging velocity, is greater than the aggressive bubbling velocity, which is greater than the minimum fluidization velocity. Sorry. Now, question number 4. Reverse flow reactor is it preferred when concentration of the reactant is less, or is it preferred when catalyst deactivation has to be prevented, or is it for low pressure drop which is desired, or is it option D, different section of the reactor needs to be operated at different temperatures? So under which of these condition is a reverse flow reactor preferred? So the answer for this is for a catalyst deactivation. When catalyst deactivation has to be prevented, this reverse flow reactor is preferred. In what happens in reverse flow reactor? In reverse flow reactor, initially the reactant goes through one side. For example, at z equal to 0, uh, if for example in the case of the axial flow, so the reactant flows through the starts going from z equal to 0 to z equal to L, and after a certain period of time, what happens, the flow is reversed. That means the reactant starts flowing from z equal to L to z equal to 0. This is what happens in a reverse flow reactor. So this change of this mode of changing the flow from a entry point of the reactor from z equal to 0 to z equal to L at different time points is it is very useful in preventing catalyst deactivation. Why is it so? So especially in case of an exothermic reaction, there is always a temperature increase along the length of the reactor. So this temperature increase, what does it so it may have an impact on the catalyst property. So for example, if the temperature increase is much higher than the it comes closer to the melting point of the catalyst, then there will be a loss of catalyst, right? And the catalyst gets deactivated, right? So in order to avoid that, if we start maintaining a particular frequency, then the temperature over the entire time span, since the flow is reversed back and forth, the temperature is maintained, and this the surface life of the catalyst is also maintained. And also this also helps in avoiding it helps in maintaining the safety conditions, especially when the temperature increases uh, very high. So when we reverse uh, the reactant flow, what happens then, the temperature rise is maintained well within the reactor, and uh, it does not cause any you know uh, explosion, or any safety concerns. So this is where the reverse flow reactor is preferred. So what kind of a reactor is preferred? For example, in the case of a concentration of the reactant is less, when the concentration of the reactant is less, a counter flow reactor is preferred. Here what have a counter flow reactor. So counter current flow reactor, what happens in case of a counter current flow reactor? In case of a counter current flow reactor, say for example there are two concentric cylinders. So the reactant in the inside cylinder goes in one direction, say from z equal to 0 to z equal to L, whereas in the reactant flows from uh, you know z equal to L to z equal to 0 in the other concentric pipe. So the reaction passes through the first inner diameter and then through the outer diameter by which the lean reactant concentration can be supported, because this will actually preheat the fluid which is necessary to increase the reaction rate of the particular reaction. Or this is also called, helps in, it is nothing but the autothermal operation. So when it goes through the inlet, so the temperature slowly increases in the inlet and in the inner diameter, and when it goes through the outer diameter, as the reaction proceeds and the reactant flows out, that temperature in the the inner tube is transferred to the outer tube, or from the outer tube to the inner tube. So there is a heat transfer between the inner and outer tube, by which the temperature support can be given and an autothermal operation can be maintained, and that thus helping in the increasing the reaction rate by giving a preheating operation. And what kind of a reactor is preferred in case of a low pressure drop? In low pressure drop, a radial flow reactor is preferred. And what kind of reactor is preferred when different section of the reactor is needed to be operated at different temperature? In such conditions, we can go for a multiple bed reactor. So the bed one, uh, it will be operating at a particular temperature, then it passes through some unit operation, and then it enters through the bed 2, and then from there it goes to the bed 3 after passing through another unit operation process. So this is how the different temperatures can also be maintained, and also it can be helping in improving the conversion also, to achieve the desired conversion of the reaction. Okay, now let's go on to the question number 5. The type of operation in a fluidized bed reactor where the gravitational flow is greater than the drag force exerted by the gas phase is called. So what happens when the gravitational force exerted by the particles in the fluidized bed reactor is greater than the drag force of the upcoming gas stream? What happens in that case? So in that case, what happens? It operates as a fixed bed operation, because since the gravitational force of the particles is greater than that of the drag force of the incoming gas stream, the gas stream is not able to fluidize the particles, the catalyst particles. So the catalyst particles are stagnant or fixed in the reactor, and the reactor operates under the fixed bed operating condition. Now let's go on to question number 6. Kuhn-Levenspiel model assumes solid flow in emulsion phase behaves like a dash. We have seen in a fluidized bed reactor, so the bubbles are formed during the fluidization process, where these bubbles have different phases. So it will have a wake in the bottom of the, in the rear end of the bubble, where the solid is concentrated, and then a cloud phase, And then finally a emulsion phase. In the emulsion phase and in the emulsion phase is where the reaction actually takes place. So the mass transfer happens from the bubble to the mass transfer of the reactant happens from the bubble phase to the cloud phase to the emulsion phase, and the mass transport of the products happens from emulsion phase back to the cloud phase and back to the bubbles. This is how it happens. So in Kuhn-Levenspiel model, the solid flow in emulsion phase behaves like what? What is the assumption made in the Kuhn-Levenspiel model? The assumption made is that it is assumed as a the solid flow is assumed as a plug flow. It moves as plugs. The solid moves as a plugs in the emulsion phase. This is what is the assumption made in the Kuhn-Levenspiel model. Now let's go on to the question number 7. Question number 7. This is actually a GATE question asked in GATE 2015. A cylindrical packed bed of height 1 meter is filled with equal sized spherical particles. The particles are non-porous and have a density of 1500 kg per meter cube. The void fraction of the bed is 0.45 and the bed is fluidized using air which is having a density of 1 kilogram per meter cube. If the acceleration due to gravity is 9.8 meter per second square, the pressure drop across the bed at incipient fluidization is dash. So, what are all the information given? They have given the bed height to be 1 meter and it is filled with equally sized spherical particles. And the density of particles is 1500 kg per meter cube. Now next, the density of air is 1 kg per meter cube. And the void fraction is given as 0.45. So, how did I write that it is minimum fluidization? Incipient fluidization is nothing but the fluidization at the minimum. That means minimum fluidization is same as the minimum fluidization. So, they have asked the pressure drop across the bed at minimum fluidization. What is the pressure drop at minimum fluidization? And also, we have made an assumption that the void fraction of the initially packed fixed bed, because they have given the void fraction of the bed is 0.45 and we have assumed that the void fraction does not change when there is a minimum fluidization. So the void fraction of the minimum, the fixed bed is equivalent to that of the void fraction of the bed at minimum fluidization, and that is why we have written that void fraction at minimum fluidization is 0.45. And they have also given acceleration due to gravity g is equal to 9.8 meter per second. Now what are we supposed to find? We are supposed to find the pressure drop, that is delta P. So your delta P the relationship is given by, so this is based on the gravitational force. So delta P by H is equal to G into 1 minus void fraction at minimum fluidization multiplied by density of the catalyst minus density of gas. So what are the known parameters? We have the height of the bed 1 meter. We have acceleration due to gravity 9.8 meter per second square. It's actually 9.8 meter per second square. Okay. It's 9.8 meter per second square. And then they've also given the density of particles as 1500 kilogram per meter cube and the density of air is also given 1 kilogram per meter cube. We have to just plug in everything into the equation. What I have done here, I have just brought in the height to this side. So delta P is equal to H into G into 1 minus epsilon at minimum fluidization into rho C minus rho G. So 1 into 9.8 into 1 minus 0.45 into 1500 minus 1, that gives around 8079.61 pascals. This is what is the pressure drop for maintaining a minimum fluidization in the bed. Okay, now let's get on to the question number 8. A bed of spherical glass beads having a density of 3000 kilogram per meter cube and diameter of 1 millimeter and bed porosity 0.5 is to be fluidized by a liquid of density 1000 kilogram per meter cube and viscosity of 0.1 pascals again. Assume that the Reynolds number based on particle diameter is very small compared to 1. If acceleration due to gravity g is equal to 10 meter per second square, then the minimum velocity required to fluidize the bed is, what is the minimum? So they have asked what is the minimum velocity required to fluidize the bed, or what is the minimum fluidization velocity. This is again a GATE question. This is asked in GATE 2012. So how do we solve this problem? Here again, what are the parameters given? So they've given bed of spherical glass beads. So the density of bed of spherical glass beads is 3000 kilogram per meter cube. And then diameter of the spherical glass bead dp is equal to 1 millimeter, which is nothing but 1 into 10 power minus 3 meters. And then bed porosity is epsilon EMF is equal to 0.5. Here again, they have not given clearly whether it is a settled bed porosity or is it porosity at minimum fluidization. So they have just given bed porosity. So we are assuming it to be the porosity at minimum fluidization, or we can assume it as the porosity at minimum fluidization is same as the porosity of the fixed bed. Because even in the fixed bed, when you pack different particles, there will be some voids. That is what happens in case of a packed bed reactor, right? There also we use the void fraction. So the same thing. And then they have given the density of liquid rho f is equal to 1000 kilogram per meter cube, and viscosity of the liquid mu is equal to 0.1 pascal seconds. What are the information they have given? They have given that they've also given the acceleration due to gravity. Here again it is it is 10 meter per second square. And the additional information, which is a very critical information, is they've given is Reynolds number is less than 1. So for Reynolds number less than 10, the minimum fluidization velocity UMF is given by UMF is equal to psi into dp the whole square divided by 150 into mu whole multiplied by g into rho c minus rho f multiplied by epsilon mf power cube minus 1 minus divided by 1 minus epsilon mf. That is, so this is the equation when the Reynolds number is less than 10. So obviously in our case we can use this equation because they have given Reynolds number is less than 1. So what we have to do, we have to substitute all the parameters into this equation. So here psi is the sphericity. So what is sphericity value in this case? They have given it is a spherical bead. So obviously the sphericity is equal to 1. Alright. So we have the diameter of the particle. They have given it as 1 millimeter. Acceleration due to gravity, we have the data which is 10. They have given. And then the density of the glass beads is also given as 3000 kilogram per meter cube, and the density of fluid is 1000 kilogram per meter cube, and the viscosity of fluid is 0.1 pascal seconds. And the bed porosity at minimum fluidization is 0.5. So substituting the values, you get minimum fluidization velocity is equal to sphericity 1 into diameter of the particle 1 into 10 power minus 3 the whole square divided by 150 into mu is 0.1 multiplied by G is 10 and rho C multiplied by rho C minus rho F, that is 3000 minus 1000 multiplied by 0.5 cube, because the bed porosity is 0.5, so 0.5 cube divided by 1 minus 0.5. So you will end up with the minimum fluidization velocity to be 3.3 into 10 power minus 4 meter per second. We require very small velocity of the order of millimeters, right? It's 0.33 millimeters actually. Sorry, 0.0003 millimeter per second. So we need very small velocity in order to fluidize this bed. Okay. Now let's get on to the final question of this session. In a particular reaction in fluidized bed reactor, the bed height is increased thrice as that of the settled bed height. If the height and porosity of the settled bed are 100 centimeter and 0.3, find the porosity at the current fluidization condition. So we have a fluidized bed reactor where there is a fluidization happening. That means some gas is fed in through the reactor to make the particles to get suspended, making it to become fluidized. And because of this gas flow, the height of the bed, the height of the settled bed is increased to 3 times of its height when it is fluidized. And they have also given that the porosity of the settled bed is 0.3. Now we have to find out under the fluidized condition what is the porosity of the bed. Now, so the solution is given the settled height of the bed is HS is equal to 100 centimeter, that is nothing but 0.1 meters. Settled porosity epsilon s is equal to 0.3 they have given. So height of the bed after fluidization is H is equal to 3 times the settled bed height, that is 3 into 100, that is equal to 300 centimeter, that is nothing but 0.3 meter. So now in order to find out the bed porosity under the fluidized condition, we have to bring in the relationship that whether it is going to be the settled bed or the fluidized bed, but the mass of the solids are not going to change, because whatever mass is kept in is only fluidized. That means the mass of the bed before and after fluidization is going to be equal, right? That is what I've mentioned. So now equating the mass of the solids for settled bed and after fluidized condition, so it is rho C into AC into rho C is nothing but your density of the catalyst. AC is the area of the cross section of the reactor, and HS is the settled height of the bed into 1 minus epsilon s, where epsilon s is the settled porosity, is equal to again rho C into AC, where again rho C is nothing but your catalyst density and AC is your area of cross section of the reactor, and H is the height after fluidization at any point of time, and 1 minus epsilon, where epsilon is the porosity at the at any point of time t. So we can cancel rho C and AC right on both sides. So we will end up with Hs into 1 minus epsilon s is equal to H into 1 minus epsilon. So rearranging this, 1 minus epsilon is equal to Hs into 1 minus epsilon s by H. So which is equal to, we have Hs is 0.1 and epsilon s is 0.3. So 0.1 and H is equal to 0.3. So that is equal to 0.1 into 1 minus 0.3, 0.3 divided by 0.3. So which gives 1 minus epsilon as 0.23. That means your porosity at the given condition of fluidization, where your bed height becomes thrice that of the settled bed height, is 0.77. So as the bed height increases thrice, your porosity becomes 0.77. Right? So this is all about the this week's uh, practice assignment questions. Thank you.